In this video, we're going to go through categorical data transformation for model preparation. So specifically, we're going to look at nominal transformation, and we're also going to look at ordinal transformation. And ultimately, this is twofold. One, we want to make sure that all of our categories are well represented. We want to make sure that we don't have multiple categories that are that are telling the same story, or introducing the same information into the model. And also, we need to numerically encode our categorical data so that we can use it in our linear regression model. One assumption is that all the variables have to be in quantitative form. So how do we represent categorical data in a numerical form so that we can ultimately use it in that model? So for this nominal transformation, we're looking at a variable masonry veneer type. So whether you have stone, brick on the outside of your home, brick common, which is like fully wrapped brick face, which is just like one front wall that's brick, or no masonry veneer. So you have another type of siding on your house. So for the nominal variable masonry veneer, we have an underrepresented category. So this is really categories that have fewer than 30 observations. It shouldn't be fewer than 20. And we'll talk about, I'll introduce the theory that says we need to have 30 observations in just a second. So why do we care? Because categories that have too few observations cannot be used to represent the population of those categories. It would be like saying I randomly select 8 freshmen at KSU to represent all the freshmen at KSU. You guys are such a diverse student body, it wouldn't be appropriate to base all of our conclusions on the population of freshmen at KSU based on just a randomly sampled group of 8. So it's just too small of a sample. So that said, the magic number in statistics is 30. If we randomly select 30 things for a category that is generally large enough to represent the population due to a theory called the central limit theorem and an idea of sampling distributions. That's not something we cover in this class. If you took Stat 1401, you probably did touch on this a little bit. But ultimately, if we continue to take multiple samples from a population that have at least 30 observations, then the sampling distribution of those groups will be normal or unimodal and bell-shaped. So 30 is the magic number that we use, and that's why in a lot of the previous assignments I have asked you to call out those underrepresented categories because we got to do something about them. Okay, so in this, we see that brick common has less than 30 observations. All the other categories have enough representation to stand on their own. So what do we do? Okay, so we can combine them with other similar categories, either by description or similarity in their relationship to the target. So that would be similar means and medians. So if we look at our brick variable up here, we have brick common, we have brick face. Those are both regardless of how many observations there are, they both represent a brick style of masonry veneer. So we could combine those two categories based on their label and based on what we know about them. The other option is to combine that brick common with a category that has similar measures of center and spread. So if we look at brick common, the most closely associated category would be the none category. It's the closest mean, it's the closest median. In fact, they're really not that far off at all. They have similar standard deviation and interquartile ranges compared to the other categories. So we could also combine it with none because of it is introducing very similar information as a whole. So that is a choice of the analyst and how they want to do that. And then the third option is just to delete that brick common category altogether. We've talked about the dangers of just starting to delete data because we could end up losing a lot of valuable information if we have multiple variables that we're doing this deletion technique with. So you just have to, you can try all three and see how they perform in the end, which is usually what we'd probably do in practice. or you can just pick the most logical option to you at the time. So I would choose the first option because it makes sense to me. 15 observations, not overly impactful. The best way to do this is with those nested if statements like we did in the transformation lecture. So in a new column, we would use the formula, okay, if the original variable equals brick common, then give it a brick label. If the original variable equals brick face, give it the brick label, otherwise return itself. So essentially you'd end up with 3 categories: stone, brick, and none. And then fill that through the data. Okay, the last step after you combine categories is to dummy code. So remember that this linear regression model requires that all these variables be in a numerical format. So for nominal variables, we use dummy coding because there is no natural order of these categories, and we don't observe, we can't assume that there's an increasing or decreasing relationship through those categories. So after combining the categories, we have 3 categories left: brick, stone, and none. So in order to dummy code 3 categories, you only need 2 dummy variables. So it's however many categories you have minus 1 is the number of dummy variables that you'll create. So the 2 dummy coded variables are the ones that we'll use in our final model. We won't use this original one. We'll use the stone dummy and the brick dummy. And we'll use none as our reference category, this one in gray. So we're ultimately telling the model either it has stone masonry or not, and either it has brick masonry or not. Okay, so why do I not need 3 dummy variables if I have 3 categories? Well, we're only going to be introducing these 2 categories of ones and zeros. It's kind of like an on and off switch. So when the model encounters a 1 for the stone dummy, it's going to turn that switch on and say, okay, this house has stone veneer on it. If for the brick dummy, if it encounters a 1, it's going to say, okay, this house has brick veneer. If it's 0, then it either has none or stone. If it's 0 over here, it either has none or brick. Okay, so how does the model know that it doesn't have masonry veneer at all? Well, if you look at this, the model would encounter a 0 for stone dummy, it would encounter a 0 for brick dummy, and so this combination of 2 zeros would indicate that there was no masonry veneer. So a 0 and a 1 indicates brick, a 1 and a 0 indicates stone, a 0 and a 0 indicates none. So that's why we only need these 2 categories. But ultimately, we want to reduce the categories, make sure we don't have any underrepresented categories, and then we'll dummy code. The other thing that we might want to consider is if we have categories in here that have the same means and medians, the same measures of spread, we might also want to combine those categories to reduce the dimensions of our model. We don't have that in our example here, but that's something that I want to empower you to do. If you notice that 2 categories are essentially saying the same thing, they're essentially saying they have the same average, the same median, the same standard deviation, the same interquartile range, we can combine those categories because they're introducing the same information into the model and we don't need to keep them separate. So our overall goal is ultimately to create the best performing model with the fewest number of dimensions or the fewest number of variables. We'll talk a little bit about the curse of dimensionality when we get to the modeling module, but those are the reasons why. Okay, for our ordinal transformation, each of you, depending on which variable you had, should have seen this increasing or decreasing nature through the categories. As we increase the quality of the house, the average sale price also increases. Now, we might have seen varying degrees of variability in the data. A lot of those variability issues are because that underlying sale price variable is skewed to the right. So we see greater variability when we have higher sale prices and less variability when we have lower sale prices, consistent with the scatter plot of living area and sale price, consistent with a lot of all of these other things that we're seeing. So just know that you've transformed that sale price variable, and these unequal variances that you see, or these unequal measures of spread that you see through these categories, are also going to be corrected with that transformation of the sale price variable. So when we see this, when we have an ordinal variable and we see an increasing or a decreasing relationship, and not only that, but that the measures of center and spread increase by approximately the same amount, it's kind of like this consistent step up or step down in the measures of center, then what we can do with that variable is what's called rank coding. So if we don't see this increasing or decreasing nature, we're going to have to dummy code it just like we did with the nominal variable above. But when we see this increasing or decreasing pattern, we can do what's called rank coding. Now, first, we're going to have to take care of any underrepresented categories. So if we have an ordinal variable, the underrepresented category has to go in a category that's adjacent to it, so to the left or to the right. So we would put this fair category in with this average category, okay, because that is the next category above it. We couldn't put fair with excellent. That wouldn't make sense. We would have to combine it with a category that's right next to it, either on the left or the right. So there's no category that's below fair, so there's no opportunity to combine it with anything on the right. But we do have that category to the left, average. So we combine fair with average. Again, the other option is to delete the fair category. We've talked about the dangers of just starting to delete data. So we'll try to combine it first. Now, if you have multiple categories for the same variable that are underrepresented, you can combine those categories together in an other category. But if you don't, you'll want to choose a category that is most similar either in description or in relationship to your dependent variable. So there's one underrepresented category, fair. In this case, we would definitely want to combine fair and average together into a single category called average and below or other. If we have any adjacent ordinal categories right next to each other in that order, and we have very similar measures of spread, we should also combine them. So if we had two categories next to each other and they had the same means and the same medians and similar measures of spread, we would also want to combine them because they're basically telling the same story. They're introducing the same information. That's not the case here, but if we did, we would want to combine them before ranking the categories. So the best way to do this, again, is with nested if statements like we did in the variable creation lecture. I should say variable creation, we're in the data transformation. Or I think we did discuss it in the background lecture as well. In a new column, we use the formula, okay? So if the original is excellent, then return itself. If the original is good, then return itself. Otherwise, put it in this other category or this average and below category and fill it down through the data set. So when we do that, we get this. Let me see if I can. We get this picture right here. Okay, so we have our excellent, we have our good, we have our average and below. We see this consistent step increase in those measures of center. For the most part, the underlying distributions appear to be relatively symmetric, but also once we transform that sale price variable, we will see kind of a consistent measures of spread across as well. We ultimately want to see a consistent decrease as we move through the categories or increase depending on the order of your variables. So we can rank code them with the variables excellent equals 1, good equals 2, other equals 3. So again, we don't need a dummy code. We can rank them because we see that consistent increase or that consistent decrease through the categories. So we would just use those if statements to say, okay, if it's excellent, give it a 1. If it's good, give it a 2. If it's the average and below, give it a 3. If we had more than 3 categories, we could continue this ranking 1, 2, 3, 4, 5, however many categories we had, and fill it down through the data set. And ultimately, we would use this ranked variable in our final model. So that's your background information. You can see excellent is 1, good is 2, typical average is 3. And then fair would also get the value of 3 as well. We don't see an example of that here, but we know that we combined those categories. Okay, so that is all your background information. In the next step, we'll actually put these into practice.